All right, let's talk about one of the most fundamental data structures in all of computer science, the linked list. Today, we're going to take a journey through its core operations. We'll figure out how to ask it questions, how to change it, and really get a feel for how it works under the hood. So, let's just dive right in.
So take a look at this. What are we actually looking at here? I mean, it kind of just looks like a bunch of numbers with arrows, right? But those little arrows, they're everything. They're what we call pointers, and they're what turn this from just a list of numbers into a chain. See, each little box, or node as we call it, has a secret. It knows exactly which node comes after it. It follows that chain all the way down until it hits, well, nothing. The end of the line, which we call null.
Okay, so before we can start playing around with this chain and asking it to do things, we've got to understand what it's made of, right? I mean, you wouldn't try to fix a car without knowing what an engine is. So let's zoom in and look at the actual building blocks.
So, every single link in this chain is called a node. And honestly, a node is just brilliantly simple. It really only has two jobs. First, it holds some piece of data. Could be a number, a name, pretty much anything. And second, it holds that all-important next pointer. You can think of it like a signpost that points you directly to the very next node in the line. That pointer, that's the magic glue holding this whole thing together.
All right, now that we get what a node is, we can actually start interacting with our list. And we're going to start simple. We're just going to read it. Ask it some basic questions without actually changing anything.
Okay, so first things first, let's ask the most fundamental question you can ask any list. How long is it? I mean, how many nodes are even in this thing? And how in the world are we supposed to count them if our only power is to move forward one link at a time?
Well, the process is actually wonderfully straightforward. Here's how you do it. You start a counter at 0. Easy enough. Then you create a temporary pointer, let's just call it current, and you place it right at the very beginning, the head of the list. From there, you just start, well, walking down the list. As long as your current pointer isn't pointing at null, the end of the line, you just do two things. Add 1 to your counter, and then move your pointer to the next node. That's it. Once you finally hit the end, whatever number is in your counter, that's your answer.
Okay, counting is cool and all, but what if we're looking for something specific? I mean, maybe we don't really care how many nodes there are in total. We just want to know one thing. Is the number 4 somewhere in this chain? Yes or no?
Hey, do you notice something? This pattern is almost identical to counting. It's super similar. You again start a pointer right at the head, and you just walk down the chain, node by node. But this time, instead of just counting, at every single stop, you ask a question, is the data in this node what I'm looking for? If the answer is yes, boom, you're done, you found it. If you make it all the way to the end of the list and never get a yes, well then you know for sure it's not in there.
Okay, so we've got the basics of walking through a list down pat. Now, it's time for a classic. This is the kind of problem you see in coding interviews all the time, and it's a really clever trick that shows you truly get how to work with these data chains. Trust me, this is where things get really fun.
So here's the puzzle. Finding, say, the third node from the beginning is a piece of cake, right? You just take 3 steps. But what if I asked you to find the third node from the end? How would you even do that? Remember, this is a one-way street. You can't just walk backward. Now that is a real brain teaser. Okay, so the most obvious way to solve this, the sort of brute force approach, is to make 2 trips. First, you walk the entire list just to figure out how long it is. Then you do a little bit of math, and you walk the list a second time to get to the right spot. And yeah, that works, but can you imagine if this list had a million or a billion items? That second trip is so wasteful, it's super inefficient. The truly elegant solution, the one that interviewers are really looking for, does this whole thing in just one single pass.
So, what's the secret? How do you do it in one pass? Well, as our source material spells out, the idea is to use not 1, but 2 pointers. This 2-pointer technique isn't just a one-off trick, by the way. It is an incredibly powerful tool that can help you solve a whole bunch of linked list problems.
Okay, check this out. Here's how it works. You create 2 pointers. Let's call one the main pointer and the other the reference pointer, and you stick them both right at the head of the list. Then, you take that reference pointer and give it a head start. You move it forward n nodes. This creates a fixed gap between your 2 pointers. And now for the cool part, you move both pointers forward at the same time, one step at a time, keeping that gap between them perfectly consistent.
And this is the magic moment. The second that reference pointer, the one you sent ahead, finally hits the very last node of the list, you stop. And where do you think the main pointer is? Because of that gap we created, it's sitting exactly on the nth node from the end. Voila! A perfect single-pass solution. It's just a beautiful, beautiful example of clever algorithmic thinking.
Okay, so we've gotten pretty good at reading and asking questions about the list in some pretty clever ways. But what happens when we actually want to change it? Let's take a look at how to correctly and safely delete nodes from our chain.
So imagine your task is to completely demolish this list, free up all the memory it's using. Sounds simple, but there's a huge trap waiting for you. If you're standing on a node and you delete it, how do you get to the next one? You just destroyed your only map. It's like sawing off the very branch you're sitting on. You'd be totally lost.
The solution is all about looking before you leap. It's simple. Before you delete the node you're currently on, you absolutely must save the location of the next node in a temporary variable. Think about it like this. You write down the address of the next house on a slip of paper before you demolish the house you're standing in. Once that next address is safely in your pocket, you can go ahead and delete the current node. Then you just plot out that slip of paper and move on to the next one. You just repeat that process all the way down the line, and you'll safely wipe out the entire list.
Phew! Okay, we have covered a lot of ground here, right? We've learned how to count, how to search, that super clever two-pointer trick, and how to delete things safely. But why does any of this matter? Why is it so important to know these specific ways of doing things? Well, it all boils down to two words: efficiency and performance.
So let's just lay it all out in a quick cheat sheet. Take a look at the time complexity column. You see that O of n for everything? All that means is that the time it takes to run these operations grows in a straight line with the number of nodes. A list twice as long will take about twice as much time. That makes sense. But now, look at the auxiliary space column. That's the real hero. It's O of 1, which means constant. It means the amount of extra memory we need to do our job doesn't grow at all, no matter how huge the list gets.
And that right there is the crucial takeaway. That's the whole ballgame. Even if our list has a billion nodes, these algorithms only ever need a tiny fixed amount of extra memory to work with. Just enough space for a pointer or two. That's it. The memory usage doesn't scale up with the list size. And when you're dealing with massive amounts of data, that kind of efficiency is not just nice to have, it's absolutely critical. So there you have it. You now have the fundamental toolkit for working with linked lists. You get the core patterns for walking through them, finding things, and changing them in a smart, efficient way. Which leads me to a final thought for you to chew on. That two-pointer trick was incredibly powerful, right? It elegantly solved a tricky problem. So what else could you do with two clever pointers? What other complex problems, like, I don't know, detecting if a list has a loop in it, or finding the exact middle of a list, could that same technique unlock? That's where the real fun begins.